Alrighty, welcome everyone to the complete course videos. We'll be talking a little bit about functions and polynomials today. Great, so let's kind of go into a little bit about what we'll be chatting about today. So we'll be talking about a couple of the topics from functions and polynomials, and then we'll kind of be talking about a little bit more about specifically going a bit more into polynomials, including how to graph them, how to factorize them, etc. So within the lecture today, we will learn how to define a function and what's the definition for a function. We'll talk about how to write and understand set notation and use interval notations to talk about our domains and ranges and be able to talk about maximal domains and calculate ranges. We'll understand how to identify and graph different polynomials and how to characterize polynomials into different groups. And then we'll talk a little bit about solving and factorizing them, and there'll be a couple questions, multiple choice and short answer questions kind of throughout the lesson today, which will just be about all of these different topics, and we'll learn how to approach these types of questions and chat a little bit about those as well. Great. So first of all, we'll kind of just chat a little bit about what is a function in the first place. So a function is defined as a type of relation between ordered pairs or coordinates where we have y values kind of assigned to x values and so we have y values assigned to x values, and it's normally between an ordered pair. So what we call our y value is going to be our dependent value, and then our x value is going to be our independent value. For different functions, you're going to have different values, so you're going to have different letters for these values. A common other example is something like time, which can be your dependent value. And when you're talking about applying it to different topics like motion or kinematics, sometimes you'll be dealing with things like that you treat x as your dependent value, so you're treating it as your y-axis, and t will be your independent value. Other examples include when you're sometimes talking about areas or volumes, and you might be comparing that to the height or the radius or a certain side length. So in terms of how we actually write out functions, so this is the notation we kind of use to write out functions, and we can see that there's a couple of different components to it. So essentially you start off with a letter, so that F is probably the most commonly one used when we talk about things like inverse functions or composite functions or derivative functions. You can do the same thing here. So essentially, if you're dealing with an inverse function, you'd put an inverse 1 at the top here. If you're dealing with a derivative, you might put a dash there. And if you were dealing with a composite, you might have your f of g kind of in there or your fog there. So you can kind of manipulate that however you want, and that's just going to be the name of your function without the x component. Then you're going to pop out the domain. So the domain can either be, we'll talk a little bit about what a domain means in a couple more slides, but essentially your domain is just going to be the range of values which your x or your dependent value can take. And then you have your B, which is your codomain. So this in most cases, or basically in all cases, will just be R in most circumstances. So this will just be R for most functions. And in the universe of methods, and in the universe of Spesh as well, in the universe of VCE mathematics in general, you're always just going to be dealing with R here. So you can kind of keep that as is. And there probably, when you go into university maths or delve a little bit deeper, you might be dealing with different codomains, but just for now you can kind of ignore it and just always say it's your domain to R. Alright, then you give a comma, and then you just put out whatever your rule is. So you have fx equals to a rule, and remember that in terms of function notation, if you want to start talking about y equals to blah blah blah, just make sure to write out that you're letting your y equal to your f of x, and the only reason for that is just to make sure that they know exactly what variables you're talking about. And that's in general for a lot of things. If ever you're going to introduce a new variable that they haven't explicitly stated throughout the statement, it's always really useful to just make sure that you state to them exactly what you're dealing with and what you're working with, and what each of them mean. Okie dokie. Alright, so what kind of determines whether a function is, a function compared to a relation, because we said it's a type of relation, right? So functions can either be one-to-one or many-to-one. What this actually means is that it needs to either have one x value for any one y value or many x values for any one y value, i.e. you can't have multiple y values for the same x value, and that's really the only requirement that it has. So the other one is a one-to-many, and how you can remember it is just like if you're talking about the axes, right? How I remember it is, the top axis is your y-axis, bottom axis is your x-axis, and you always list coordinates as kind of x, y. So if you want to be talking about this thing, what I think of is that your first one is your x coordinates, and your second part to your, something to something is your y coordinates. So you can kind of see that you'll have many x coordinates to this one y coordinate, and that's the scenario that you'll be able to have. So i.e. we want a graph like this where we can see, oh yeah, so we have multiple y values for the same we have multiple x values for the same y value, which is entirely fine. But what we don't want is something like this one, right? Because you can see that there's multiple x values, there's multiple y values for the same x value, and that's just not acceptable for us. So this would be called one-to-many instead. And if it's something like this, it's simply just going to be a relation rather than a function. Common example of what we deal with these ones are things like circles. So you'll be expected to graph a circle, which is a type of relation, but it's a common type of relation that you'll be expected to graph just throughout the year. And the main thing about those is that you don't ever call it a function because it's not technically a function. And the vertical line test is how you can test it. So if you draw a vertical line, like the name suggests, and it hits more than one point, that function is no longer a function, it's just a relation. Okie dokie. Alright, so let's talk a little bit about set notation and how it works. So a set is a collection of unique things. For our purposes, we'll be talking about numbers. So a set for us is going to be a collection of numbers. Couple of different notations that we use for set notation. So we have E, which is it's an element of. So often what we say here is something like X is an element of blah, to say that that's its domain. We have this kind of backwards dash, which is related to excluding. So if x can take, a certain amount of values except for a couple of values, then that gives you your excluding point. And the last thing is, if we're dealing with kind of using set notation quite exclusively, normally if you want to list individual elements, so for example, x can equal to 2, 4, 6, 8, or 10, 12, whatever, the main thing is to use these curly brackets. So you'll have something like, so if we pretended that our domain of x was from, was 2, 4, 6, 8, we could do that there. And you can kind of see how here we'll say that our x kind of belongs to 2, 4, 6, 8. Or sorry, 2, 4, 6 rather than 2, 4, 6, 8. There's also a couple of standardized sets that you will see in methods in general. So what you'll be dealing with, and the key thing is that you need to just have an idea of what each of these mean. So for real numbers, that's probably the one that you're going to come across most commonly. I'd say real numbers and integers are probably the two that you'll see the most overall. And so real numbers are everything that's on the number line, so every number you can imagine is a real number. Rational numbers are things that you can write as a fraction. So essentially it can't be a third, it can't be something like Euler's number, it can't be pi. So it must be something which can be written either as a fraction, which means that it's either going to be a reoccurring decimal or it's going to be just a decimal which ends. You can also write integers, so integers is often a common example, a common thing that's used as well, and it's represented by z. And you have n for natural numbers, which you don't actually see that much around of, but it's just good to be aware of what it means. And then if you want to talk about positive or negative of a set, all you need to do is just pop a, let's say we're talking about all positive real numbers, all you have to do is pop a little positive at the top there, or negative depending on what you want. But the important thing about this is if you talk about negative or positive, this thing does no longer include 0. So that's a really important thing to remember. So R positive includes everything from 0 upwards essentially. Alrighty, so then we'll talk a little bit about interval notation. So interval notation is, so we talked about before how we can use those kind of curly brackets to list individual numbers, but if we want to talk about a range of values or, a continuous set of values, so for example we want numbers from 2 to 4, it's going to be really, really difficult to list out all of the different values, and in fact it's going to be impossible because you can go 2.000001 and still never really get to the point of it, right? So the important thing is that we need to have a measure which can list every single little value that occurs between 2 points, and how we can do that is by interval notation. So interval notation is kind of like the corresponding part to inequalities. So it's perfectly fine if you want to, using your set notation, you can still use inequality notation if you would like to, but I find that interval notation is often a little bit cleaner and easier to write. And all you have to really remember is that there's a couple distinctions. So there's kind of only three key rules from this. These are all the examples so that you have them on hand and you know how to represent it, but there's only 3 key rules to this. So the first rule here is that so if the number is not included, so for example every number up to 2 would mean that 2 is not included, right? So if you're not going to include that final number there, the most important thing is you're going to put a round bracket. If you want to include that number, so up and including 2, it's going to be a square bracket. And the other key thing to remember is because infinity, technically we can never really get to infinity or get to negative infinity, that's always going to be a round bracket. Alright, so let's talk a little bit about domain and range and how that works now, and why it's important. So domain is essentially going to be related to having a set of x values for which f is defined. So it is the set of dependent values for which f is defined, or for which your function is defined. So for example, if we were looking at something like this, right? If we wanted to figure out what the domain of something like this was, we need to figure out, what restrictions on the domain exist. And with domain, for most functions, they have an unrestricted domain. So for most functions under the sun, we can pretty happily say, yeah, the domain is R if they don't really tell us anything. And in fact, the domain for this one is R. However, for something which had some functions do have restricted maximal domains, and particularly I think the 4 functions that you should be a little bit aware of are if you have things which are denominators, so commonly hyperbolas, so 1 over something, 1 over x or 1 over something. The second example are surds, so if you have root x. The third example are tan functions, which are circular functions, which we will also chat about, in one of these lessons. And there will be tan is one of the ones with asymptotes, and that's why we have restrictions on the domain. And the last one is logs, which has a restriction on its domain for x as well. So those are the 4 that commonly occur. Within the universe of kind of polynomials and power functions, the main 2 you're going to be dealing with are these hyperbolas and surds. So if you're looking at a hyperbola, the main thing is to have the denominator not equaling to 0. So you want to make sure that that denominator never equals to 0, and that's your main point. Whereas for your square roots, this number can be bigger or equal to 0. So you just essentially want to make sure that that number never falls below 0, because otherwise your square root is going to be undefined. Just to flag here, but there'll be, specific lessons on exponentials, logs, and the circular functions. But for the tan function, essentially the base tan function, it's that you won't have values occurring at x equals to pi and 2, x equals negative pi and 2, and that's just because of the asymptotes which exist there, because the tan function is equivalent to sine over cos, and at those points the cos equals to 0, and it kind of plays back into this one once again. The log function, for the base log function, your x must be bigger or equal to 0, so it just must be bigger or equal to 0, rather than compared to this one, which is, not bigger or equal to, x must be bigger than 0, full stop, compared to this one, which must be bigger or equal to 0. And then we have our range, which is denoted by ran, f, or ran, whatever the function is. And it's a set of all the y values that f can take, or the set of all the y values, or all the values that the dependent value can take. And for this one, if we have a look, you can see there will be no potential y values below -4. So in fact, your range here is actually going to be just -4 to infinity, and we're going to include the -4, putting a square bracket there. And that's essentially just because the -4 can be included here, because we can see that evidently it's included as part of the graph as its turning point. Alright, so all about polynomials. So the first fact about polynomials is that the degree of the polynomial is the highest exponential. So if you have an x to the power 4 in there, it's going to be a quartic. If you have an x to the power 3 there, it's going to be a cubic. So we will talk about each of these different polynomials. So polynomials are essentially just positive power degrees. So linears, quadratics, cubics, quartics, etc., etc. In the universe of VCE Maths, really what you're going to be dealing with is up to quartics. Do not panic if you get something which is like x to the power 5 or x to the power 6. It doesn't actually matter too much. You know all the skills already that you'll need to know for everything. So anything above a quartic won't really give you any extra idea. There won't be any extra concepts involved in it. It will just be extra annoying to do, essentially. So we'll start by talking about each of these. So we'll talk more specifically about quadratics in the next slide, particularly how to solve them and how to, utilize them properly. You'll see as we step up the functions, the less and less we have to actually know about these functions. So the linears we have to know the most about, and that's why there's going to be a dedicated lesson on them. But quadratics, also one of the functions that we have to know quite a bit about, and we can do quite a bit with as well. Cubics less so, and quartics even less so. Okay, so in terms of graphing a quadratic, the main thing is there's two ways to graph it, essentially. Kind of similar, I guess, but you can either try and find the x-intercepts first, and then from the x-intercepts, because if you plus the two together, the midpoint is going to give you the x-coordinate of the turning point, and you can find the turning point by that and pop that in, and just make sure to find, like for all graphs, finding your x-coordinates, finding your y-coordinates, and then, finding your special point here, which is your turning point. And the main thing is just making sure you have that, where that turning point is. So another option is you can find the turning point turning point first, and then from there you can also find the x-intercepts if you would like to do so. And yeah, just assume for most polynomial graphs that they want whatever they need labeled. So they need the special point and they need the x and y intercepts labeled. Alright, so let's talk a little bit about these couple of functions now. So we can see these are all different cubics, right? So we have f, g, h, and they are all you can see that they all have slightly different shapes. So there are three types of cubics. Really, the one here, the f of x cubic, you don't see around that much, and that's essentially because it looks like it has a non-stationary point of inflection. So it's kind of doing a little bit of a wiggle, but not really much, and that's why it looks a little bit strange, right? The main two we deal with are kind of these two. So either we have a point of inflection, which is what's happening here, so we can see it's inflecting at that point. And this will only ever occur if you have something called a perfect cubic, i.e. you have a cube by itself, so something cubed plus a constant. If you can't manipulate it into that form, you won't be able to get you won't be able to get a point of inflection. If that's not possible, what you'll get is something like this. So you'll get two turning points, and essentially how you work this out is you just factorize the function, and from there you can find the two turning points. Once again, important points to label are x and y intercepts, and the turning points here unfortunately don't fall exactly on the midpoints between the intercepts. So what you have to do instead is you have to find them via calculus, and what you do is you can do differentiation and find them via that. And you can kind of see the three different types here. Alright, so let's talk a little bit about quartics. So quartics are quite similar to cubics in their approach. Really what you're wanting to do is finding the x and y intercepts and finding the turning points or points of inflection. The extra little bit here is that technically it can have a turning point and a point of inflection. So if your quartic is perfectly factorizable into that special form where essentially you have x plus something to the power 4 and then you have a plus a constant, that's just going to revert to look something like a quadratic, and it's just going to look like it's in turning point form. If you have one factor repeated 3 times, what you're going to get instead is a point of inflection-y type thing. And then if not, you're just going to get 3 turning points which kind of go up and down like that. And if you look at the ends, you can see that this one's a positive one, whereas the one that looks like a kind of an M is the negative one because the ends are pointing down. That kind of gives you a bit of information about what's going on. The key thing here is you use calculus to figure out where each of these points are. Another thing in general, just for graphing and doing this type of thing, is something which is, something which really helps with the graphing. If you have a linear turning point, it's going to just go straight through it like that, and that's just because it's linear. If you have a quadratic, a quartic, so anything even powered turning point, you're going to have a bouncing off, a turning point at that x-intercept. And then if you have an x-intercept which is anything to the power of 3, 5, 7, so any odd power except for 1, you're going to have a point of inflection at that point. So as long as you remember those 3 key things, it really helps you to graph out all of these a little bit more appropriately. Alright, so let's talk a little bit about quadratics. There's 2 key concepts I want to talk to you about here. So the quadratic formula, know it, love it, learn it, essentially. It's going to be something which is really helpful and often a go-to method for solving quadratics. What's really important that you can take from it is that concept of the discriminant, which is essentially that b squared minus 4ac component. So if it's equivalent to 0, this thing would disappear. So you're just going to get negative b over 2a as your solution. If it's smaller than 0, you have a negative surd, which is not possible. So that's why you have no solutions. And if it's bigger than 0, that means that you're going to have both the plus and the minus. So that means that you're going to have 2 solutions, and it's going to be possible to do. You can also use this quick test to figure out whether your function is factorizable or not. So if you put this in and it's a perfect square, that means that you should be able to factorize your function relatively easily. If not, always just go with one of these methods to figure out exactly what your solutions are, because it might just be a little bit too difficult trying to factorize it if this is not a perfect square, because then you'll end up with a surd anyway. It's probably not worth your effort trying to go down one of those branches to factorize it really nicely. An alternative method is kind of completing the square, which I'm not sure, I like quite a lot. Sometimes it gets a bad rep, but essentially the idea is it actually is the thing that produces the quadratic formula. So you start off with something which is x squared plus bx plus c, and then what you want to do is kind of take the a out to make sure that you have that bit. Some people take a out of the whole thing. I just take a out of the first two components because you're going to take it out and then put it back in for the c anyway, so I just leave it outside. Then what you want to do is half the x component and square it, and then minus that square. So what you're doing is you're, like the name suggests, completing the square. So you're aiming to get a perfect square, and then what you're going to do there is, because now you're aiming to get a perfect square, once you get that perfect square, you've now added in a random constant. So that means that you need to take it back out to make it all nice and pretty. So that's what we do here. We'll make it a perfect square, and then you can kind of solve that equaling to x, which will give you solve that equaling to x, and that will give you the quadratic formula right there. Alrighty. Alright, so let's jump into talking a little bit about some questions. So which of the following functions satisfies the following equation f fx equals to x for any real number x? So this is from 2014 VCA exam 2. So what we want to do here is essentially all we have to do is to plug in each option. Because we have calculators for this, it's probably a lot more rapid and you can just pop them into your calculator quite quickly. But there is also a couple options that we can rule out quite quickly, right? So this is the type of question I would recommend actually trying to do in your head during reading time, so you can scribble away once you start writing, because that minimizes the amount of time that you spend doing kind of questions, and that means that you might have time left over at the end to kind of go over questions. So the correct option here is E, and we'll talk about why. So for the first option, if we were to plug in that into the f of x, what we would have is 2 times 2x, right? Because we're just plugging f of x into the position of x. So what we'll get here is that it will just equal to 4x. For the second one, if we do the same thing, so it's kind of quite similar here, we'll have x squared squared, right? So that will give us x to the power of 4. So quite the same, we're just plugging x into x again. This one, there's not really anything to plug it into, right? There's no x component, so it would just not really be the x anyway. It would just always be 2 root 2, regardless of what we're dealing with. For the third one, we have x minus 2 minus 2 again. So essentially the minus 2's are going to double up here, and we're just going to get minus 4. That compared to the last option where we have kind of the 2 and the x swapping positions. Now we'll have 2 minus 2, which kind of gets rid of the 2, and we'll have minus minus of x, which leaves us with 1 x component. So you can kind of see that it would be the last option here. And it'd be quite quick to just pop these on all into your calculator and have a go, but you can tell that the mathematics of this isn't too difficult to do in your head, and you could have a think about doing this type of question in your head before your writing time started, within your reading time, and that's just to increase efficiency of your answers. Alright, another multiple choice question. So consider the function hx 4x minus a over root x plus 1. A belongs to R, and the maximal domain of h is given by. So this question focuses on maximal domain that we talked about before, about the implicit domain that's given by certain functions. Now, the main thing here is to examine about which part is the problem in the question. So what we can identify here is that the main problem is actually the denominator. The numerator won't really make a difference to the domain here. It will only make a difference to the range that you produce from it. So we have two things kind of going on in terms of the denominator. First, our denominator cannot equal to 0, and that is because it's underneath, it's the denominator, so overall that denominator cannot equal to 0. And secondly, we have a surd going on, which means that that bit must be bigger or equal to 0. That combined together will mean that the denominator, so the root x plus 1, or the x plus 1 more specifically, has to be both bigger and not equal to 0. So if we kind of figure out the intersection between those two domains, what we'll figure out is that it has to be bigger than 0, full stop. So x plus 1 has to be bigger than 0, which if we kind of move it across, we'll get that x is going to be equal to is going to be bigger than -1 when we kind of pop that across. Alrighty, so let's talk about this little short answer question. So it has two parts, and we'll chat about both, and then we'll wrap up after that. So we have this polynomial of 3x cubed plus 5x squared minus our kind of mu x minus 12. And this shares all three x intercepts with our other function, which is essentially going to be our 3x to the power of 4 minus 25x cubed minus 66x squared plus 148x plus our lambda. So the question here is asking us to find the x coordinates of any additional intercepts of y equals to p of x that is not shared with y equals to q of x. So the strategy here is going to be that we can see that there is one step power difference between those two functions, right? So if we want to figure out the additional intercept, all we would have to do here is actually figure out what the additional one is, so that extra one is, and the simplest thing to do for that is just going to be to do long division. So what we have here are our two functions, right? So what you can do is you can kind of group your functions into x1, x2, x3, and then you have your final ax plus b, right? So this one is one of the methods which essentially we've done equating of coefficients across, and what you can see here is they've made this essentially equal to that, and you can see that all of those factors are shared all throughout. And what you're going to do here is just essentially equate coefficients across. So what you're going to say is that it's going to be this function q of x times ax plus b is going to equal to your other function, and then once you kind of equate coefficients and kind of move things across, so you can see that this would give you 3x to the power of 4, right? 3x to the power of 4, and then plus 3x plus 3bx to the power of 3, right? 3bx to the power of 3, and then you'll end up plus your 5ax to the power of 5ax to the power of 3 as well, and you can equate coefficients kind of across there and see how it's equated across. So essentially you can write out all of the coefficients and just use that to equate. Alternatively, kind of a method that you can use from a topic called partial fractions is essentially just sub in a value for x, because remember, it's not the x things that you're really focusing on here, it's going to be related to the other values that you're actually going to be focusing on, right? So what you're going to do here is you can just put that across, and you can kind of see that you'll have your negative 12b equaling to that, so you'll get each of your values kind of equaling. And what we want to do is also try and avoid this mu and lambda type concepts, because they want exact values for your a and b, i.e. they want the extra intercept. So the main thing is just trying to avoid the lambda terms and the mu terms for now. So essentially what we're going to get is that our remaining term is going to equal to x minus 10. So we'll have an intercept at 10, 0. Alright. So the next one kind of asks us to determine the values of lambda and mu, which we've essentially already done kind of in the previous question, right, through our equating of coefficients. So all we need to do is kind of continue that. So what we're going to do here is we've ended up with the equating of coefficients, and we're just going to equate the x squared term, which will give us negative lambda minus 50, which will equal negative 66, so we'll get our mu will equal to 16. And then if we talk about our lambda, so our lambda was equivalent to negative 12 times our b, so therefore we can just times our b in, and that will give us 120 as our lambda. Alrighty, so to chat a little bit about what we went through today, so what we talked about are our functional key features, so talking about domains, ranges, implicit domains, talking about how we determine whether something is a function or not using the vertical line test. And we also talked about the different notation that they use to describe domains and describe those types of things that can be involved in functions. We talked a little bit about polynomials, so how to graph polynomials and the key features that you'll be looking out for when you're graphing a polynomial. And also in our practice example there, we talked a little bit about how to do a bit of factorization, including talking about how to do equating of coefficients as one of the methods for factorization. We did a couple of multiple choice questions and talked about strategies or recommendations about when to do those appropriate multiple choice questions. And we did a bit of a short answer and talked about how we can answer those questions and get through those.